It's my great pleasure to introduce Eric Tonicello and Julien Duboc from ISI, Ingénierie et Sécurité Incendie in Lausanne, Switzerland. Eric Tonicello is the founder and director of this company, and Julien Duboc works there with him. Over to you, Eric.
Okay, thank you, everybody. Just to thank you for the invitation today. It's a pleasure to be there with all the SAFIR community. We'll just do a very short introduction, then Julien will present the day. Just an introduction for me. We have been working with SAFIR since more than 15 years now. We are doing a lot of projects quite every day. 3 people are working on SAFIR today. In the office, we are now 7 people. Most of the problematic today is to define the thermal action, because we do not have problem with structural calculation, but it's always with finding the correct thermal action for our scenario. So Julien will focus today on this this calculation and design, and we'll see that we've done a lot of advanced calculation for our client. So let Julien speak, and I turn off my microphone.
Yeah, okay. Thank you, Eric. So yes, the idea is to present you some interesting project in which we use SAFIR for structural calculation under fire and also CFD calculation. So let's start with this first project. We will detail a little bit more than the others. So it's a project of a transformation of the luggage handling building for the Geneva airport. So for this project, of course, there is a need to comply with the Swiss fire standards, and regarding the structure, we have a requirement of R30, 30 minutes of fire resistance. So here we have a picture of the structure. So this is a composite slab supported vertically by steel columns. And another interesting information for this case is that we have a double sprinkler installation system. So this information is interesting for the CFD model we will show in a few minutes. So we started the performance-based design study with a pre-analysis with a standard scenario with the ISO fire curve. So first of all, we check the behavior of the composite slab. So on the plan, we can see just one part of the entire composite slab, but it's still the same field, which repeats over the entire area. But this is a huge area. So we have primary beams and four external beams and 3 internal secondary beams for this composite slab. So the idea was to study the behavior of this composite slab with thermal and structural calculation with SAFIR. So first of all, of the existing situation, so without any fire protection. And what we can see here is that we observed a huge vertical displacement at the midspan of the slab because all the beam sections are exposed to the ISO fire. And we see, yes, the huge displacement up to more than 1 meters vertically. So we cannot achieve the 30 minutes of fire resistance for the existing situations. So after that, we made a second calculations with a partial fire protection. So the objective was to try to optimize a little bit the need of fire protection for the composite slab. So we will launch another structural calculation still with SAFIR, considering all the external beams fire protected and just the 3 internal beams are unprotected. And here is the vertical displacement still at the midspan of the slab, which is a bit different as the previous curve. And with this partial fire protection, we can achieve more than 30 minutes of resistance under this ISO fire. Then we check the behavior of the columns. So we have an example of one section here. There are several sections in this building, but the results were the same for all the section because all the faces are exposed to the ISI curve. So we observed quickly the buckling of the column before the 30 minutes. So what about the results after this first step of analysis? So of course, the existing situations isn't acceptable. And if we stop the study at that step, we had to say, okay, we need to protect the columns and also the composite slab, not the entire composite slab, but all the external beams. We made a slight optimization with the first step of analysis, but there is still lots of beams to protect. And as it's for an existing building, we had to protect all the beams on site. And with the occupation of the area, it's a huge work, so a high protection cost for that protection. And finally, we have the question if the fire scenario wasn't too conservative for the structure. So that's why we proposed to the client to continue the study with a more advanced study with natural fire scenario. So the idea with this second step of analysis was to take into account the real fire risk for the area. So here we have some pictures inside the building. So we can see the fire load density, which is mainly composed of luggage concentrated at the end of the different conveyor belts. We have containers, but also another kind, some trolleys. And also we have different types of vehicles just to move the containers full of luggage from the building to the planes. So we can also have a fire of a such vehicle. And as we said at the beginning of the presentation, we have a sprinkler installation system. So the idea with this natural fire analysis is to take this installation account. Okay, so after the identification of the potential fire source, we had to calculate the fire load density for the luggage. So we have only standard luggage in the area. So what we did is to use the composition for a cabin bag because it's mainly the same, but we had to adapt a little bit because in a standard luggage, we can have a bigger quantity of cosmetics on the contrary of the cabin bag. So we adapted a little bit this proportion. We'll have around 50% of the composition of plastic items, but we reduce a little bit the textile proportion just to have alcohol items, just to take into account the cosmetics in the standard luggage. So with the heat of combustion of these different items, we could assess the fire load density of one standard luggage, so around more or less 800 megajoule. And there was one fire test for a cabin bag in literature. So we use this heat release rate curve in order to make a correlation to adapt it for a standard luggage. So we get more or less 400 kilowatt of heat release rate per luggage. Now about the vehicle, we also find different fire tests in literature for forklift vehicle, but the problem for our project is that we can have a bigger size vehicle, so it's more or less a simple car, but maybe with less fire load density, but it's could be quite representative. So that's why we make this assumption. So it shows to use the well-known standard heat release rate curve for a car to take into account the fire of this kind of. It's probably a bit too conservative, but as we are on the safe side, it's quite okay for the Swiss authorities too. So we different for the study. So the first one was to consider that at the end of the conveyor belt, we can get different containers in which, containers which are full of luggage. And the idea is to consider one luggage in fire at the beginning, and in order to have maximum thermal stresses to the structural elements, we located one column just in front of the first container. So that's our first scenario. So we have the real representation here. So we have to imagine that that all these containers are full of luggage. The second one is quite the same, but it's not for containers, but for trolleys. So the main difference is that they are open over the entire area. So we thought it was interesting to study this scenario because it can be a bit different regarding the thermal stresses received by the structural elements if the fire was contained in a closing box or on the trolleys where where the trolleys are open over the entire area. So it can be a bit different. So still a fire luggage as an ignition source and near a steel column. And finally, the third scenario, which is quite the same, but instead of having a luggage fire source, we have a vehicle as a fire source. So here is the CFD visualization of the simulations that we made with FDS. So we can see this behavior a few minutes after the start of the simulation. So we can see the high flame lengths. We could explain that because just a few minutes after the fire could spread inside the box, because we have around 40 luggage inside the containers. The fire can spread very easily, and we get a very high heat release rate in the container. So that's why we see this kind of fire. A few minutes later we observe the activation of the sprinkler installation because we modeled directly the sprinkler in FDS. So the idea was to check the influence on the sprinkler over the thermal stresses received by the structural element, but also to see the influence on the fire spread. We can see here that the fire spread occurs. We will just discuss about this. So how can we explain the fire spread even if we have a sprinkler installation? One first assumption we chose is the ignition temperature, because at the beginning of the simulation we considered only the fire of one luggage, and just to take into account the possibility to the fire to spread, we imposed an ignition temperature on each luggage. We chose this value 300 degrees because in the luggage we can we saw that we have different items. We can have plastic items, textile, alcohol, or papers or cellulosic materials. So we chose the values, the lower values between these different items, because 300 degrees is quite representative of the ignition temperature for cellulosic materials. So it's probably a bit conservative, but one more time we are on the safety side with this assumption. And another explanation for this fire spread, with this scenario, we consider the fire inside a steel box, inside steel container. So finally, the influence of the sprinkler on the fire is quite limited, because there is no real interaction between the low gauge in fire and the droplets due to this box. So we still have an intense radiation even if the sprinkler activated. So it is just visualization of the thermal stresses during the simulation. So we can see that we have locally very high temperatures between 700 and more than 1,000 degrees locally. And in order to have more accurate data, because the objective with this approach is to couple the CFD results to SAFIR to study the structural behavior of the slab and also the columns. So we use different adiabatic surface temperature devices located at different position on the columns, also on the slabs and the sailing beams. So we use the same structural model as for the ISOFIRE, but we adapted the thermal calculations. So we impose as boundary condition the different AST curves we calculated with FDS in order to study the behavior on the natural fire scenario. So this first calculation, so it's representative of the existing situation, so without any fire protection. So we see that the resistance of the composite slab cannot be achieved with this scenario. So we launch another simulations still for the slab, but considering the protection of the external primary beam only, so all the secondary beam, internal and external, are unprotected. And with this optimization of the fire protection, we can ensure the fire resistance over for this scenario. And for the column, it was the same result as for the ISOFIRE. We saw the high temperatures locally, so the columns are a bit sensitive to this kind of thermal stresses. Very quickly, so here are the same kind of result for the other scenario. Just the difference is that for the trolleys, we have less luggage on each trolley. So when one trolley is on fire, there are lower each release rate. So we can see this with quite moderate temperatures comparing with the previous scenario, and still with the adiabatic surface temperature curves. We use it to make a structural calculation with SAFIR. The difference is that as we have moderate temperatures, we can ensure the resistance of the slab without any protection. But for the columns, we have still the same results. So the conclusions. So we made an advanced study in several steps. So before we made any study, the client thought he has to protect the entire slab. So after the first step, we saw that we could optimize a little bit, protecting only all the external beams. And after the final step of analysis, we could optimize a little bit more, protecting only the primary beams for the sailing, and of course the columns, all the steel columns. So that's all for this project. Just a few words about other interesting project in which we used SAFIR calculation. Maybe some of you heard about this project because we already presented in previous conferences. This is for an existing tunnel. So there is a tramway project for this existing tunnel. The particularity is that this is a tunnel under Geneva Airport, so under the runway. We have the runway here in blue and the tunnel here in yellow. So here's the structure of the existing tunnel. This is a pre-stressed concrete structure in that direction. We have also rebars in both. And the idea was to model the structure of the tunnel and check the behavior on the fire, because we can't have any displacement for this tunnel. We can imagine why. We cannot stop the Geneva activities. So like the previous study, we made two main steps in this analysis. First step with standard fire curves, with the ISO curve, RWS curve, which is more adapted for tunnel, and also with natural fire curve, so with fuel tanker, heavy good vehicle here, and for the tramway. So we used FDS for the natural fire curves. And when we checked the behavior of the existing structure, we saw that except for the tramway, the existing situation was not acceptable due to high deformation and maybe up to the collapse of the structure. So there was a need to improve the situation. So we proposed to the client a combination of solution, passive measures, and also active measures with the water mist. And at that step, we used SAFIR calculation to design the passive protection in order to optimize the position of the passive protection in the structure, and to know which thickness we have to plan to get lower displacement in case of fire. And last word about this final project. This is for an hospital in Geneva. So the project was to transform the different levels of the hospital. So we used natural fire scenario, not CFD model at that time. We used just zone model, because we can see here with the fire plan of the project, we have simple geometry, simple fire compartment, so we could use zone model to that. So we analyzed the situation for different fire load density. The blue curve is for the real fire load density, and we wanted to challenge a little bit more the structural behavior of the slab. So that's why we check for different fire load density. So to do that, we use one more time SAFIR with a more advanced concrete slab. So we represented just one part of the slab in order to hit just one part of it, representatively with the fire compartment. And another part remain cold, and we check the behavior. And finally, the conclusion for that study is that we could prove the fire resistance of the concrete slab thanks to the natural fire scenario and without any protection. That's all for us. Thank you very much for your attention, and with Eric, we are ready to answer your question.
Thank you very much, Julien. Thank you both, Julien and Eric. We have a couple of questions on the first example that you discussed. Could you please comment on the structural design of the floor, or interested in the
Yes,
cross-section and the reinforcement details?
I can share. So I think it was for the first study. So for this slab, the primary beam were not connected to the slab. We have only connectors to the secondary beams. So that's why we concluded that the primary beams were more vulnerable than the secondary beam. So that's why after protected these beams, we get better behavior on the fire.
I see. Thank you. But
So,
what is the slab, the floor design in that?
It's a composite slab. So we have a deck, steel deck with a hollow rib deck, and concrete slab and with rebars.
And reinforcement in the concrete.
Yeah,
do you know the amount, or do you have a sense of the amount in square millimeter per meter?
No, sorry, I don't have the information in mind. Yeah, no,
Thank you.
Yeah.
Because I was interested. So in the end, if I followed your design, you were able to leave the peripheral beam, but secondary beams unprotected, right?
Yeah.
And there's a question from Chenji, also related on that. What was the applied load on that floor system for that type of building? Was it heavily loaded?
Not really. It was yeah. We have office on the upper levels of the buildings. So the loads are quite low.
Okay. And because some of the peripheral beams are unprotected, we are assuming that they are larger displacement than if they would be protected. Did you observe any displacement at the top of the column, or were they pulling on the columns?
With that model, we don't really study the behavior of the column, because we know that we had to protect them, but maybe we could observe maybe a compression located around the column. So maybe we could model the 3D for the column in the model, maybe to check if there is a behavior a bit different. It could be an optimization of the model.
Thank you, Julien. And we have another question from Nacho from Valencia about the tunnel, because you didn't have too much time to discuss the tunnel, obviously, but can you just comment on how you handle the soil? And did you use the springs to represent the effect of the soil? Did you apply any horizontal loading? Or what was the boundary conditions basically there for a tunnel?
Yes. For this structure, we use a simple model. So we used replacement load replacement force in order to take into account the pre-stress cable. So we adapted the force at each time of the simulation. So in order to take into account the thermal elongation of the cable. So yeah, we adapted the force, and also we get horizontal force at each side of the tunnel to take into account the soil.
Thank you. Thanks a lot for the presentation again. I think I missed one question in the chat, but we'll go to the next speaker. If you have the chance to answer in the chat, of course,
yes,
that would be great as well. And it's nice to see all those questions. Of course, feel free to interact using the chat, or you can follow up with emails. For the sake of time, we're going to go to our next presenters. Thank you again, Julien and Eric, so from ISI in Lausanne in Switzerland.